So we'll start a new chapter, which is metal. Again, this is an important chapter. The percentage of the marks compared to the overall exam paper, you will find greater weightage or percentage or questions from this chapter. First, the reactivity series. The reactivity series of the metal is, please send cats, monkey and zebra in large high cage. Make sure pets locked. So the first letter of each word is representing an element. P means potassium, S means sodium, C means calcium, magnesium, aluminium, zinc, iron, lead, hydrogen. But hydrogen is not a metal, so but this is important to know the position of hydrogen. Then copper, mercury, silver, gold is also there, but you're not studying gold in detail. So, and then the last one is platinum. This is a reactivity series of the metal. And you should know the position of carbon as well. The carbon position is between aluminum and zinc in terms of reactivity. So as we go down, what we observe, the reactivity decreases. Like it will become less reactive or they don't react easily as we go down in this series. Same thing, stability of the metal. Stability of the metal increase as we go down the group. What is the meaning of stability of metal increase? Like, for example, you have potassium and you have platinum. Because potassium is, if you available like in the surrounding or atmosphere, oxygen is available. Because potassium is more reactive, so potassium instantly will react with oxygen, and as a result it will form potassium oxide. But because platinum is less reactive, it does not react, so it will remain in the element state. So potassium is less stable metal. In terms of stability of the metal, potassium is less stable and platinum is more stable. So as we go down in this series, the stability of the metal increases. Like in the element state, we can find them easily. Is it clear, this statement, the stability of the metal? And going down the group, what we observe going down in this series, stability of the compound decreases. So more reactive form a more stable compound. So when we compare, like example, if you have two compounds, one is potassium oxide, another one is mercury oxide. Which compound is more stable? Like when I supply heat energy, can remain in a compound state for a longer, for a higher temperature. Which compound is more stable, potassium oxide or mercury oxide? So potassium oxide is more stable. It will remain in this state for a longer period of time when we supply energy. So this is first thing, like the reactivity series, you should learn the reactivity, you should know the trend. As we go down, the reactivity decreases, stability of the metal increase, stability of a compound also decreases. So more reactive metal forms stable compounds as compared to less reactive metal, because they don't tend to react easily. That's where the compounds are less stable. Take the screenshot of this and then we'll move on. Then the second is reaction of metal with acid. In this chapter, you will find many tables are there which you have to learn. So reactivity series, which involve potassium, sodium, aluminum, lead. So reaction with acid, till lead, they all can react with both concentrated and dilute acid, form salt and hydrogen. So whenever these metals react with acids, like even if it is dilute or concentrated, the results will be salt and so below lead, they can react with concentrated acids only. There is no reaction with dilute acid, they can only react with concentrated acid. And in the lab, because we are not using concentrated acid, that is why their reactions are not common in the lab. This is a reaction of metal with acid. Then reaction of metal with water or steam. So again, we have a reactivity series. Because hydrogen is not a metal, that's why I did not include in this series. We are discussing the reactivity of the metals. So what will be the result when these reactions occur for potassium, sodium, and calcium? They can react with cold water. Cold water, it's not like ice cold water, it's water at room temperature refers to cold water. So it can react with cold water. And what will be the product? It will give metal hydroxide plus hydrogen. This will be the product when it react with cold water. Like example, if potassium react with cold water, it will form potassium hydroxide plus hydrogen. If the sodium react with cold water, sodium hydroxide plus hydrogen. And calcium react with cold water, calcium hydroxide plus hydrogen. From magnesium till iron, they can react with steam only. Means react with water at high temperature. So basically, because of high temperature, water converted into steam. And as they can react with steam, as a result, what it will give? It will give metal oxide plus hydrogen. And for lead and below, there is no reaction with cold water or steam. Does not react with water at all at any temperature. So again, you have to go through this and learn that what will be the result when acid is reacting with metal and when water is reacting with metal. Then the reaction of water with metal oxide, reaction with oxygen to form metal oxide. Again, the reactivity series. So reaction with oxygen. So till iron, when they react with oxygen, it will form metal oxide. But below lead and copper, what it will do, it will only form oxide layer. Like the whole metal is not converted into metal oxide, only the top surface is converted into oxide layer. What's the difference? Look, for example, if I have a piece of potassium, this is the potassium. So when it reacted with oxygen, the whole potassium reacted with oxygen. As a result, it will turn into potassium oxide. The whole potassium reacted with oxygen, and as a result, it turned into potassium oxide. But when we have elements which are below iron, like lead, copper, they're not forming the whole metal oxide, only the surface. Like example, if you have, say, copper. So this is copper. So when copper is reacting with oxygen in the atmosphere present in air, so oxygen react with copper, but only the surface turn into copper oxide, and remaining it remain as a copper. The surface only turn into copper oxide. This is also refers to like rusting or corrosion. Yes, iron forms the rust on the surface. What happened in case of iron? Actually, it's not like directly the whole iron is converted into. If you have a piece of iron, I will explain that example of iron. Look, example, you have a piece of iron. This is iron. And in our atmosphere, we have oxygen. So this oxygen react with iron. So first the top layer turn into iron oxide. But when you see this iron oxide reddish brown layer, this iron oxide which is formed is a porous. Porous means there are small holes are there, so which reduce the strength. So as it reduces strength, so whole iron will get turned into iron oxide. It's not like only the surface. When it is started with the surface, but if you leave this iron for because it's a slow process, not a fast process, but if you have a piece of iron and you leave it for a longer period of a time, this whole iron will turn into iron oxide. So this is not happening only for surface, this happens that whole iron turned into iron oxide. But in case of like if you have a piece of copper or silver is there, only the surface will have an oxide layer. The surface will turn into oxide and the other will not change. The inside part will not change into oxide. But in case of iron, zinc, aluminum, if oxide layer is there, with the passage of a time, the whole will convert into oxide. Is it clear? Is it clear this part? Take the screenshot of this one. The thermal stability of the compounds. Thermal stability refers to the temperature. By supplying a heat energy, if we can carry out a chemical change, we call that as a thermal decomposition. And if a substance decomposes at high temperature, we call that is higher thermal stability. So in this part, you will learn the thermal stability of metal hydroxides. Thermal stability of metal hydroxide means when we supply heat energy to the metal hydroxide, what we will observe, and this is according to the same reactivity. So if we have potassium hydroxide, we have sodium hydroxide, calcium hydroxide, magnesium hydroxide, aluminum hydroxide, zinc hydroxide, iron 2 or iron 3 hydroxide, lead hydroxide, and copper hydroxide. So when we supply heat energy, why I did not write for mercury, silver, and platinum? Because they're hydroxide, they're unstable compounds, so does not exist. So it's easy to remember this table. When we supply heat energy to potassium hydroxide or sodium hydroxide, they are stable to heat. Means by supplying a heat energy, I cannot carry out a chemical change. I cannot decompose this potassium hydroxide or sodium hydroxide. We can melt them, but we cannot carry out a chemical change. But when I heat hydroxide from calcium to copper till copper, so it is easy to remember from C to C, like starting with calcium, ending till copper. So when we supply heat energy, what it result? It will result in a formation of metal oxide plus, because temperature is high, so it will be steam, but I'm writing water, so you remember that H2O will be there. But it was in practical, it is a steam because of water vapors due to high temperature. So if I heat any of these hydroxide from calcium till copper, the result will be metal oxide plus water. So if I supply heat energy to calcium hydroxide, so what will be the product when I supply heat energy? So it will form calcium oxide plus water. If I supply heat energy to lead hydroxide, so what will be the result? It will form lead oxide plus water. Same thing if I supply heat energy to aluminum hydroxide, the result will be aluminum oxide plus water, or basically due to temperature it is steam. And for the last one, these hydroxide do not exist. Is it clear? The result, when we supply heat energy, it will form metal oxide plus hydrogen. Then you should be able to write a balance equation. Why the last three hydroxide does not exist? Do not exist. What's the reason for that? As we discussed earlier, if you remember the reactivity series, so we have more reactive metal at the top of the series and less reactive metal. So they're not able to react with, because how hydroxide or can be formed by reacting with oxygen, by reacting with steam normally. So mercury, because it is less reactive, so as it is less reactive, it is not reacting with, you can see here this part, no reaction with water or steam. So if it is not, they are less reactive, so it does not react. That's why it cannot form the hydroxide, because there is no reaction. If the reaction occur, as we go down, the reactivity decrease. So how the metal tend to react? By they tend to lose electrons. But these metals, they are not able to lose their electron easily. That's why they are not reacting. So as they are not reacting, the new substance is not formed. That's why their hydroxide do not exist. Is it clear the reason? But you should be able to write the balance equation. So we have this equation: calcium hydroxide on supplying heat energy form metal oxide plus steam or water. This type of reaction, when we have one reactant and more product, this type of reaction is known as thermal decomposition. How you'll identify thermal decomposition? Only one reactant is there and more products. Because when you supply heat energy, you decompose this calcium hydroxide into calcium oxide plus steam or water, we call thermal decomposition. I have to balance this equation. So to balance this equation, we always start with oxygen, followed by hydrogen, and then other element. So first we check oxygen. How many oxygen on our left hand side? How many oxygen are there on the left hand side? So two oxygen on the left, and how many oxygen on the right? Two oxygen on one with this calcium oxide having one, and water is also having one. So total it will be two. So you can see two oxygen right, two oxygen left, oxygen is balanced. What about hydrogen? Two hydrogen on the left and two hydrogen on the right, so hydrogen is also balanced. And calcium is one, and calcium is one, so calcium is also balanced. So actually this equation is balanced in terms of calcium, hydrogen, and oxygen. So you don't have to put any number. When you complete an equation, it turned out to be balanced equation. Is it clear how the equation is balanced? When we complete a product, because the result should be metal oxide plus water. So when metal oxide and water are or steam is formed, When we write a balance equation, complete the equation, we found that the atoms are also same on the left and the right hand side. Is it clear, this part? Take the screenshot. I'll share another link because this session will end less than a minute.